Hello and welcome back. Nice to see you again. That's all I wanted to say. Let's get started. In this video, what we're going to be doing is visualizing time as a structure in 3D. And to do that, we're basically going to treat time as data and then bring in tools from data science. We're going to use these tools to take that data and represent it and convert it into this structure in 3D. Okay, so the idea is you've seen these like counters that count up hours, minutes, seconds. So that generates this list of unique timestamps, right? One for every second. So what would happen if we treated each of these timestamps as a point in space? What would that set of points look like? How would that set of points be arranged in space? This was the question that I'm trying to answer in this video. The most obvious way to plot this in space is to treat the hours as the x coordinate, the minutes as the y, and the seconds as the z. And so when you plot this, you get something that looks like this. Over time, it traces out these sheets, one sheet per hour. The sheet is composed of 60 vertical bars, so there's 1 bar per minute. When you plot out the first 12 hours of a day, you get these 12 sheets. With this plot, like there's nothing too crazy happening yet. This is kind of like what we would expect. But what happens now if we include days in addition? Like days, hours, minutes, and seconds, that gives us a 4-dimensional set of points. And what would that look like when we bring that into 3D using dimensionality reduction? In order to visualize that in 3D, we're going to use the one and only t-SNE dimensionality reduction algorithm. I'm going to give you a quick explanation, a quick intuitive explanation of how this algorithm works, because we're going to use that algorithm to create the visuals for the rest of this video. So this is, look at this wonderful prop that I made. This is a visualization of what's happening in t-SNE. In this algorithm, we want to get a set of points that reflects something about the structure of the higher dimensional set of points. We can't really see what's going on in here in the high dimensional space, but we can measure the distances between all these points very, very simply. Just the same way you'd measure the distance between 2 points in 3D, you know the distance between every pair of points. What this algorithm is going to do is that it's going to place a rubber band, a force between every pair of points in the embedding space. Using this information of the distance, that force is going to be proportional to this distance. These two, the pink and white points here, it's telling us that they're pretty close in the high dimensional space, so we're going to have a really tight rubber band there. And then likewise, the blue to white is like a little bit longer, so we're going to have a looser rubber band there. This is an algorithm that happens iteratively. It happens over time. Over time, these points are going to self-organize. They're just going to arrange themselves, acting under these forces until it kind of comes to an equilibrium. I actually have a visualization of this I did years back. It's a totally different data set, but it incidentally also has this like 2-dimensional sheets property in it. At the beginning of the algorithm, the points start out in completely random locations, and you can see how they kind of very quickly start to organize themselves into the shape. And that reflects what's going on in the higher dimensional space. It's beautiful. Let's see what happens when we take our 4-dimensional set of timestamp vectors here and put it through t-SNE, just totally as is. What happened was a little bit surprising and it confused me at first, because you're still getting these sheets, but when you colorize by hour, these are not 1-hour sheets. And this is what happens when you colorize by minute. And surprisingly, when you colorize by second, we find that each of these sheets represents 1 second of time. Any one of these points, any one of these sheets contains like the second, for example, second number 2 from minutes 1, 2, 3, 4, 5, 6 and hours 1, 2, 3, 4, 5. Because this is like a really non-intuitive representation of time, I started to wonder, how can we change the data going into t-SNE in order to get something that looked like the original thing we had with these 1 hour sheets. With the 1 hour sheets, 2 consecutive seconds were next to each other, right? It gives the sense of seconds being smaller than hours. This is what I decided to do, and this is what actually works. This is what the table looks like, starting at 12 a.m. and going all the way to 11:59 and 59 seconds over 2 days. You can think about adjusting these numbers. First of all, we can normalize each of these columns. We're just going to divide by the max in each column. So now in this normalized table, you have you still have 60 seconds per minute, 60 minutes per hour, but now the value ranges between 0 and 1 in all columns. And then you can kind of scale it again. I multiplied the seconds column by 1/12, the minutes by 1/4, and the hours by a half. Now that kind of matches our intuition of like seconds being smaller than minutes and minutes being smaller than hours. It turns out that when you do this rescaling and then you put it into t-SNE, you recover the 1 hour sheets. The idea is that by doing that scaling, you cause the seconds to range over a smaller value than the minutes, and then the minutes to have a smaller range than the hours. Explaining it in a different way, when you just put this version into t-SNE and ask it to embed this, your seconds are ranging from 0 to 60. So it's viewing these seconds as being really, like each of these timestamps as being really far apart, because you're telling me the value is going from 0 to 60. Meanwhile, the days is only going from 0 to 1. It doesn't know that this column represents days and this one represents seconds. It just sees the value. That's why we have to do this scaling, this adjustment, to make it artificially like seconds are smaller. So now the days are the biggest change. When it goes from 0 to 1, that's like a big jump. To summarize, like depending on how you normalize those columns, you can get all sorts of different shapes. Yeah, I think that's it. Let me know if you had any questions. I know this was a really, this was a kind of mind-bending one because it involves dimensionality reduction and working with these numbers. But thanks so much for listening, and we'll see you next time. Peace out, guys.